Everybody talks about AI hallucinating. So why does AI hallucinate? All large language models like GPT-4, Claude Sonnet predict one token at a time. And when those tokens agree with what we want or what's true in the world, we say it's awesome. When they don't agree, we call it a hallucination. And here's the thing, because they're always predicting one token at a time, you could say that all large language models do is hallucinate. It's just sometimes they happen to be correct. So let's go back to our sentence, the capital of England is. And like I said, all these large language models generate one word or one token at a time. So they need to generate the next word, and even if we only have two words to choose from, London and Paris, and even if London has a 99% probability of being chosen, one time in every 100 will land on Paris. It will choose Paris. And that's what these models are doing. They're picking the next word according to a set of probabilities. And in practice, there's thousands of words to choose from, not just two, each with a probability. So even if the likely one, the one we think is not a hallucination, has a very, very high probability, sometimes the model picks other words. And that's why they hallucinate. So let's dig into this. First of all, let me explain tokens. So there are over 600,000 English words. That's a lot of words if we are predicting one word at a time. And if we're building a table of all these probabilities, that's a lot of probabilities. So to make it slightly simpler, large language models predict tokens instead. Tokens are often like words, they're punctuation, sometimes they're a full word, and there's different tokenizers that exist. They can break a large text down into tokens. Some of these have 50,000 tokens or 100,000 tokens. That's still a lot, but it's a lot less than 600,000 words. So we have a set of tokens that we're trying to predict. And what happens with big words is, or long character sequences, is they get split into many tokens. So here I made a word up, and you see for the tokenizer I'm using, it split it into 5 tokens. Bolicious! Exclamation mark. And this way we're dealing with a limited set of tokens, 50,000 in this case. So these large language models are trained on a lot of data. Often the entire web, lots of books, lots of code repositories, secret data. But we're going to do something simpler to show you how hallucination works. And what we're going to do is for every token, I'm going to find the probability of the next token. So for example, if you give me the word the, then I'm going to count the number of times the is followed by cat, the is followed by dog, the is followed by house, and so on. And by counting all of these things up, I can get a probability. If I see the word the, I can say the word cat is next with a probability 1%, 10%, whatever that is. And I'm going to do this for all 50,000 tokens in the vocabulary. I'm going to look through a large set of data and I'm going to count how many times one word follows another. Now I don't have a huge amount of resources. I'm not going to use the internet for this. Instead, to do all those counts, I'm going to use the Sherlock Holmes mysteries because that's a much smaller data set. So let's try it. So when I go through the Sherlock Holmes mysteries and I look at the word the, or the token the, I count the number of times that it's followed by every other token. And here in this table you see the top words. So whole is the most frequent, the whole, the same, the room, the matter, the time, and so on. And what we're going to do is we're going to use these counts and we're going to use them to generate text. So if we see the word the, we're going to predict whole with probability 1.9%. If we see the word the, we're going to pick same with 1.8% and so on. So some of the tokens will have very, very low probability. We may have only seen the and then that token once in the whole data set. But it could be picked. Because what we're going to do to generate new text is we're going to take this table and we're going to roll some dice. And the dice is going to be weighted according to all these probabilities. And the one that we land on is the one that we'll use to continue the text. So we don't pick the top probability each time. We're not going to predict whole every time we see the word the, because that will lead to very, very boring text. We're going to weight our dice according to these probabilities and pick one. So the most likely will get picked the most often, the least likely, the least often, and so on. So for the word the, or the token the, I have 50,000 rows, one for each of my other tokens. And I do this for every token. So I have 50,000 tables, each with 50,000 rows. That's 2.5 billion probabilities. But even for modern computers, this is very simple. I can do it very easily. So let's see what this looks like. So we start generating. We start with the word the, and we look at our table, we roll the dice, and this time the die lands on next. So that's our next word. So now we take the table for next, which has a different set of probabilities from the table for the. We roll the die again, and this time we predict a full stop or a period. So we put that down as part of our text. We do the same thing again. We take the table for the full stop, that has another set of probabilities. We roll the die and we get with. We do the same thing for with and get my, and do the same thing for my and get nerves. So we can keep on repeating this, changing the table for each token and generate some text. So here we generated the next with my nerves of a revolver, but only say until this happened. So we can generate some text, but it doesn't make any sense. And that's not really surprising because we're only looking at one token each time. We're only looking at one word, predicting the next one. And of course, if you do that, you're going to get something fairly random. And this means that our context window, the amount of history of words we're looking at, is only one token. Whereas large language models can use even millions of text as a context window. So let's upgrade our AI slightly. We're going to use a context of 5 tokens. So we're going to look at 5 words, a history of 5 words, and predict the next token. So for every possible combination of 5 tokens, 4 tokens, 3 tokens, 2 tokens, 1 token, we're going to look at the probability of generating the next token. So that's a lot of tables. That's billions and billions of probabilities. But we can still do it. So now we take in the last 5 tokens of our text, we push that through, we find the right table, we still get a list of 50,000 probabilities corresponding to all our tokens, and we roll the die. So we're doing exactly what we did before. We're still just taking a list of probabilities for every possible token and rolling a dice. But now those probability tables take into account a context window of 5, the 5 last tokens in our input. So here we take the words, it was then that I, we look at the probabilities, we roll a die, and we get the word must. And now we shift our context window to the right, and we have was then that I must, because those are the last 5 tokens. We look at our new probability table, roll the die again, and we get leave. Another shift of our context window gives us a different set of probabilities using the 5 words then that I must leave. We roll the die and we get you. And we keep doing this one word at a time until we get it was then that I must leave you to your papers for a little, which is now starting to make more sense. And if we keep going, we get this. It was after 5 o'clock when Sherlock Holmes returned from his excursion. He held in his hand a sheet of blue paper, scrawled over with notes and figures. Now this is much, much better. We're only looking at 5 tokens and predicting 1 token at a time. But we can now generate text, and it sounds pretty reasonable, pretty plausible. So here's the thing. All these large language models, GPT-4, Claude, Sonnet, Gemini, Flash, are doing exactly the same thing. They can take in much larger context windows, sometimes millions of tokens, but they still predict 1 token at a time. You give it all of this input in the prompt, that goes into the model, and at the end state, it creates this list of probabilities for the 50,000 tokens or the 100,000 tokens, whatever tokens it's using. It rolls a die, and it picks the next token based on those probabilities. It then puts all of that back through itself, gets another set of probabilities for tokens, rolls a die, and picks the next one. It's doing exactly what we do here. It's just learning those probabilities for the next token in a very complex way, a very smart way, and we'll have a video on that later on. And if large language models are still a mystery to you and you really want to know all the details, or you want to learn AI and you don't know where to start, then my course, Your AI Guidebook, might be for you. You can learn AI from scratch. It doesn't require any math, any coding. Everyone can learn AI. And it's a course where we walk you through each of the components, each of the fundamentals, step by step. There's a few free chapters, so you can try it out. Click on the link in the description. Okay, so back to our 5 token probability tables. Can it answer questions? So instead of using Sherlock Holmes as the data, I'm going to use something called the natural questions dataset. This is a dataset that is used to test LLMs, and it's just a lot of question-answer pairs. So things like, who wrote about the idyllic I Live Innisfree It's William Yates. What is the name of the airport in Rome, Italy? It's Leonardo da Vinci International Airport. So we're going to train on 10,000 question and answer pairs. We'll do exactly the same thing we did before. We build these probability tables of what token follows the 5 tokens that we input. And let's see what happens. So we've trained our probability tables and we input a question. Who is the second person to walk on the moon? And we just asked the model to continue to predict one word at a time using those probabilities. And it generates the text Buzz Aldrin, which is correct. Oh my god, we've now built a sentient AI program. No. Unfortunately, we haven't. It's just probability tables. It's just a table of probabilities predicting the next word. So what happened? Well, the reason when we typed in who is the second person to walk on the moon, it gave us Buzz Aldrin, was that was in the data set. It was one of the questions, one of the 10,000 questions that we trained on, the question and answer pairs. This happened to be a question and answer. So it just so happens that the probabilities for Buzz Aldrin was very, very high. And it just so happens when we rolled the die, we picked those questions. In fact, there isn't another question that has moon as the last word of the answer. So Buzz Aldrin was extremely high. And if we ask things that are not in the data set, things that it isn't trained on, how do you get popular on TikTok? It says Billy Goat. What is the distance between London and New York? Tax revenues. So here you can clearly see we're not learning anything. We're not modeling the world. It's just a simple model and all it's doing is hallucinating all the time. But as we saw in the Sherlock Holmes example, it can be convincing. And in question and answering, when it's been trained on the data it's already seen, it looks like it's doing something. But it's certainly not sentient. It is an AI model. It's just a very, very simple one. And large language models that power things like ChatGPT and Claude are much more complicated. But again, at the end of the day, they're just picking the next token according to a set of probabilities, and they do it one token at a time. So that's really the message here. When people talk about AI hallucination, it's just because they're selecting from this probability list, and sometimes it selects a token that doesn't match the reality or doesn't match the answer we want. But still, fundamentally, this is what these models are doing. And if you understand this, it explains a lot of the behavior. Also, these models are trained on a lot of data. They're more complicated. They're trained on a lot more data. Trillions of tokens in many cases. And that means they've seen a lot of language. They've seen a lot of data. They're able to replicate that. That's why large language models appear so fluent and so reasonable all the time, even if they're hallucinating, because they've been trained on this data. There's also a lot of system processing going on in the background. It's just not the model that you're sending data to and it's returning. There's lots of tools, there's lots of other processing elements that go into an application like ChatGPT. And if you don't know about this, check the video out that I'm showing on screen now. But I hope that gives you some insight into what people mean when they talk about hallucination and how these models are just picking probabilities. And even a really simple, stupid model that's just counting words can appear fluent, can appear sentient, and it's by no means the case. So you know the drill. If you like this content, I'll be making more videos, so please subscribe.